Shall we start? Okay, so let us continue with this story that we were doing this week. So let me just again remind you that for the time being, we're just trying to understand how to compute things for the nonlinear evolution of dark matter only. We started with this simple assumption that the dark matter is ideal pressureless fluid. We derived equations of motion for fluctuations on top of some usual expanding universe background, and we saw that the equations of motion for perturbations satisfy some fluid-like, self-gravitating fluid-like nonlinear equations. Those equations cannot be solved easily in full generality, but on scales where fluctuations are small, we can do this perturbation theory expansion, and we can solve equations perturbatively. I showed you these solutions last time, and once we computed, let's say, the next to leading order correction to the power spectrum, which we call the one-loop power spectrum, we found that actually it doesn't really work very well. In particular, it doesn't get the correct nonlinear matter power spectrum measured from simulations, and computing it at even higher orders in perturbation theory doesn't improve the situation. And the second problem is that even on very large scales, when you look at the shape of the nonlinear BAO peak in the two-point correlation function, you see that this simple model doesn't reproduce it. And so today we are going to discuss how to fix these two issues. So I already told you a little bit at the end of the last lecture what goes wrong. So I told you there are actually two things that go wrong. In some sense, the equations of motion that we were using were wrong. So this, usual words that we say that the dark matter is a pressureless ideal fluid are not correct when we talk about these nonlinearities. And the second thing that goes wrong is that this solution we found in some sense is incomplete. We will see in what sense today. And crucially, the problem that arises is that, as I already showed to you last time, we were studying the properties of these perturbation theory kernels. Very generically, we know that the nonlinear couplings of small scales can affect large scales. And in principle, we have to, since on the other hand, small scales cannot be understood analytically, we have to find some way to consistently decouple the two and take systematically into account these effects of the small scales and large scales, okay? And I told you already that our idea is going to be to start with the correct equations of motion, which fundamentally really is this collisionless Boltzmann equation, and then try to find fluid-like equations of motion for dark matter, which are consistent. The reason why there will be a fluid-like description, even though we are starting from the collisionless system, is that, as I told you, in principle, the dark matter particles do not move far away in the edge of the universe, and also they group together in the dark matter halos, so this provides some kind of an effective mean-free path for this system. So then what you have to do really to find the correct equations of motion is to start from the fully true equation. This is the complete theory that you want to describe. And then if you want to write down some fluid-like equations, you have to also split things into the long wavelength and short wavelength fluctuations. And what we want to do is to somehow use this full Boltzmann equation, but rewrite it in terms of the so-called moments. And these moments are just like some integrals of the distribution function, or momentum multiplying distribution function. And of course, if you integrate over all possible momenta in a given position x and given moment of time tau, you're going to get the mass density. If you integrate the distribution function multiplied by pi, you will get the momentum, and so on. And we can then define the velocity of this fluid as a ratio of momentum and mass density. Now, crucially, we want to find only the equations of motion for the long wavelength fields. I'm going to imagine that we are splitting the fluctuations into small wavelengths, so like high-frequency fluctuations, which are on small scales, and they're the long wavelength fluctuations, which are on large scales. And we're going to focus on these long wavelength fields. And as before, what I mean by this operationally is that there is some window function. You can imagine it's a simple Gaussian, where you take the real space field y, this is some generic field, and then just smooth it using this window function. And then what you want to do is to find the equations of motion for these smooth fields. Now, I'm not going to do any of these details here because it will be just too long. But what you're going to find, and you can find all these derivations in the lecture notes that I mentioned at the beginning, what you will find is that the equations of motion for these long wavelength fluctuations look almost the same as before. So the continuity equation is identical, and the Euler equation has all the terms as it has before, except that now there will be a new term appearing on the right-hand side. And this new term, which was not there before, is some kind of an effective stress tensor, which arises due to the fact that we had to do this proper smoothing and taking into account that we're discussing only the long wavelength solutions. And you see, there are nonlinearities in the full there are these nonlinear terms in the full Boltzmann equation, and these nonlinear terms are going to produce additional terms in the equations of motion that we're considering here for the fluid. And the reason why this effective stress tensor appears is when we do the smoothing, these are non-trivial. You may imagine that if you just smooth, for example, the product of two fields on some smoothing scale R, that naively you would get only the product of two long wavelength fields. But this is, of course, not the case, because first you are doing the multiplication and then smoothing. The smoothing doesn't commute with the product, so you're going to get all possible higher derivative corrections in terms of the long wavelength fields. And also, there is always some short wavelength component of these fields where you make a product and then smooth it on large scales. Okay. So this term depends only on the small scale fluctuations, and it's a purely stochastic. This is what we were discussing last time, that if you have two very short wavelength fluctuations that combine together to produce a long wavelength field of momentum k squared, for example, by the mass and momentum conservation in dark matter case, this effect must be suppressed by k squared. Okay, and so indeed we are going to, these stochastic terms are very suppressed on large scales. Okay, so you see, like the real equations of motion were not that one of the ideal fluid, but they have some extra terms on the right-hand side. And in principle, the amount of extra terms is not fixed because we don't know how to compute, if you look at the details, you don't know how to compute exactly what this effective stress tensor is. But what you can always do is to expand it in the long wavelength fields and the derivatives of the long wavelength fields and so on to whatever order in perturbation theory you want. That you know how to do. And then there will be some stochastic small-scale contributions. But the price that you have to pay is that, in principle, this expansion is fixed in terms of the functional form of which fields and with how many derivatives enter. But there will be some free coefficients in front of these terms in the equations of motion that you simply don't know. Okay, this is what is going to happen. So I'm just writing here in Word what I just said, that this tau ij is going to be expanded, let's say, you can expand it in delta and velocities and so on, and there will be stochastic terms. And crucially, the coefficients of this expansion are unknown. And these coefficients depend on the exact details of small-scale physics. This is very similar to what happens, for example, in hydrodynamics. Also there, you can start from the exact Boltzmann equation. You can, there the existence of mean-free path is said by something else. Simply, the system is not collisionless, so the molecules can collide, and there is some notion of the mean-free path. On scales larger than the mean-free path in the fluid description is valid. You can derive similar equations where the stress tensor is fixed. It has usual viscosity terms, pressure terms, and so on. But then some coefficients in these fluid equations, like viscosity coefficients, are not known a priori. You cannot derive them from some first principles unless you solve the full microscopic theory, okay? But of course, you can measure them in laboratory. For example, if I ask you, can you tell me what is the viscosity of some fluid, let's say water? You can either do a small experiment to measure the viscosity, or you can run a big simulation where you take into account all possible interactions of molecules, and then on a computer measure the viscosity term. So for the dark matter, it is exactly the same story. It is an effective fluid on large scales. It behaves like an effective fluid. It has some free coefficients in the stress tensor, and these coefficients can be either measured from simulations or measured from the real data that we see on the sky. Now, what can be this stress? Now, in principle, you can derive the form of this effective stress tensor from the Boltzmann equation, but it's useful to think about it, maybe for the purposes of discussing bias tracers, a little bit more differently. You can ask at leading order, because I'm doing some expansion in perturbations and derivatives, you can ask at leading order in perturbation theory and at leading order in derivatives, what are all possible terms that I can write down for an object which has two indices? Here we have tau ij. And the only two options are basically something which is linear in the density fluctuations, and basically it has the same powers as delta fluctuation delta. Basically, these two derivatives of phi give you a tidal field or delta, basically, okay? And the only two options is like either to have something which is di dj phi or Laplacian of phi. And of course, there is a mistake. What is missing here is a delta function, the chronicle delta. And then there is this purely stochastic term, which comes from small scales. So there is nothing else that you can write down at leading order in perturbations and derivatives. If you want to put more powers of the density field, sure, you can write down more terms. But since fluctuations are small, then these extra terms will be small. And if you want to do perturbation theory, you always have to consistently keep as many terms as you need for a given precision that you want to achieve. So for the purposes of this lecture, it is enough to think of these leading order contributions to this effective stress tensor. And so now things are very simple. What we want to do is to go back to the equations of motion, which are almost identical as before. And so that was good because we already did a lot of work to find solutions for these equations. And the only thing that we have to modify now is to add additional source term in the other equation on the right-hand side, using this ansatz for the stress tensor. And if you do that, you're going to get basically the equations of motion, which now are organized nicely. They're written, first of all, always in terms of these long wavelength fields. So we are discussing only what we really want to measure at the end of the day. And we can, in principle, keep as many terms as necessary in this effective stress tensor, but they're organized always in terms of expansion in two parameters. One is that we can always expand in perturbations, and the parameter which controls that is the variance of the density field. And so as long as you're on scales where the variance of the density field is small, each additional power of the density field makes these terms in the equation of motion smaller than the previous ones. And there is also the expansion in derivatives. You can, for example, take certain term in the equations of motion allowed by symmetries, and which appears in the station tensor, and always add more derivatives. But more derivatives always come with a price that you have to pay. And if your scale is much smaller than the nonlinear scale, much longer than the nonlinear scale, then this will be again additional suppression that you have. So so now we have a consistent set of equations of motion. We know what are the expansion parameters, and then we can order by order in perturbation theory do any computation we want. And this framework is what is called the effective field theory of large-scale structure. The reason why we call it effective field theory is, of course, because this resembles a lot, and not that it resembles, but it's the same as what we do, for example, in any other effective field theory, like either in quantum field theory or classical systems, or even hydrodynamics. It is an effective field theory of collisional fluid. Okay. Are there any questions about this? Is the logic clear? Okay. So, as I said, we are basically going to, now here I copied the equations of motion that we had before. So this was really almost the same as before. So now we have everything in terms of the long wavelength fields. The same nonlinearities are still there, for example, in the continuity and the other equation. But we are going to have two additional terms in the equations of motion, which are called the counter terms, like in the usual language of field theory. And at leading order in perturbation theory and derivatives, there will be only one term which appears, which is like a Laplacian of delta. And then there is a stochastic term, which are just here defined to be two derivatives, the idj of the tau ij stochastic. Okay. So these are the only additional terms that we can write down at leading order in perturbation theory. So maybe just let me give you a hint that here I wrote two different terms, but this is only tau ij. So tau ij will have two extra derivatives by the time we go to the variable theta, and therefore when two derivatives act on this term and this term, they become the same and give you basically Laplacian of delta. Okay. So this is why both of these terms basically collapse into a single term here. And crucially, these additional terms are now are basically telling us how the small scale fluctuations affect large scales at leading order in perturbation theory. Okay? Because they do come from some non-trivial part of the averaging where you take into account this short and long wavelength fluctuation mixing. So in this sense, like the equations of motion that we were using before were wrong because they were incomplete. They were missing some additional terms that now we include. But also it is in this sense that I said at the very first lecture that on large scales, the universe looks relatively simple. Relatively simple meant that, yes, we still have to do with the nonlinear evolution, but there is a relatively simple way to organize, let's say, at least in perturbation theory, how the real equations of motion look like. So at each order, if you want to refine these equations of motion and make a better prediction, what you can always do is to keep higher order and higher derivative terms on the right-hand side and get a more precise answers. But at each order in perturbation theory, there will be a finite number of terms you can write down, and things are relatively simple. All the templates or spatial dependencies and fluctuation dependencies are fixed up to some unknown coefficients that have to be measured from the data. And these things depend on like really the properties of dark matter. Okay, so now once we have these additional terms in the equations of motion, then what we can do is to find the perturbative solution again. So all the hard work we did in the previous lectures is okay. So this part of the solution is still there. So the usual two loop diagrams that we discussed last time. The linear theory, of course, is always there at leading order. And then the nonlinear power spectrum, on top of the result we found last time, has two extra contributions. So from the equations of motion, these additional two terms will give you two extra contributions. One of them is proportional to the k square. This k square comes from the fact that there was a Laplacian of delta. So in Fourier space, it becomes k squared times p linear of k. And then you have another parameter multiplying the power spectrum of the stochastic part of the stress tensor. Now, again, as I said, these two parameters serve the purpose to encode the back reaction of the small scale fluctuations on large scales. And in particular, they're different because this parameter here has to do with the back reaction of small scales on large scales, which is correlated with the long wavelength fluctuations. So in some sense, you can imagine that if you have a long wavelength density field, then how small scales behave and back react on large scales depends on the value of the field. So for example, if you have an overdensity, the small scale fluctuations will behave differently than if you have an underdensity. So there is a part of back reaction that on large scales that depends on the density field, and this is encoded in this first term. Well, the second term is really something that is independent of the long value density fields, and it's a purely stochastic term. So given that it was a purely stochastic term, as we saw last time, then its power spectrum is basically fixed by mass and momentum conservation, and it must go like k to the 4. So if you go on scales k, which are much small, for wave numbers k, which are much smaller than the nonlinear scale, this power spectrum is very small and it is very subdominant. It decays very fast as you go to large scales. And usually we neglect it in the one loop calculation that we usually do, or it doesn't really matter. Other terms are much bigger than this one. So is this clear? Any questions? Okay, so another way to see that these equations of motion make a lot of sense, or addition of these terms makes sense, is to take a look at, you remember that I told you last time that when we were wondering why can we even talk about dark matter as a fluid, one of the things that I also was referring to is that even if you look at the loop calculations that we did, we see that, you remember there were some loop integrals where we have to integrate over all possible momenta, and we were not putting any UV cutoff. We were just integrating over all scales and getting some answer, but we know that our equations do not make sense of small scales. So how can this be consistent, okay? So for example, let me remind you that this P13 integral had the following form. It was some P linear of K times some perturbation theory kernel times P linear of Q, all integrated over all possible momenta Q, okay? However, this type of solution makes sense only on large scales. So on small scales, when we integrate over momenta with the high wave numbers, we are getting some answer, but we cannot trust it. This is not a trustable answer. So in principle, what we would really like to do is to maybe somehow put some cutoff here. Now, putting a cutoff explicitly is a bit dangerous because then the result would depend on this cutoff if you don't have anything else in the equations of motion. However, it turns out that nicely, as it must be, that these additional counter terms are actually serving the purpose of absorbing any cutoff dependence that you may put in your integral. And the reason is that if you take a look, let us imagine we fix k to be on some perturbative scales. So k is smaller than k nonlinear. And we are integrating over this q, over all possible q's. And when q becomes much bigger than k nonlinear, meaning that q is also much bigger than k, then you remember that we show that one of the properties of this kernel is that for this particular momentum configuration, the kernel goes like k squared over q squared, okay? So you can see that the overall momentum dependence of this integral P13 is k squared times P linear of k times some number, which is the integral over some powers of q and then P of q. So if you put the cutoff dependence, there will be some dependence of this number on this cutoff, but the functional form where you have k squared times P linear of k will always remain the same, okay? You can check that numerically. I mean, I'm simply just saying like a trivial thing. In the high q limit, this function is very simple. So if you change the cutoff in the high q limit, you're going to get a different amplitude, but the k dependence is always going to be k squared times P linear of k. On the other hand, this free parameter, the counter term multiplying this fixed form, which we derived from the effective stress tensor, has exactly the same functional dependence. So it is also k squared times P linear of k. And when you sum up the two contributions, any choice of lambda is okay, because whichever choice of lambda you make, your coefficient CS will adjust to match your choice when you compare your theory to the data. Okay, so what should be always the same is the sum of these two contributions. And when you compare it to the data, whatever cutoff scale you use to compute this contribution, first contribution, you will adjust CS in the fit to have the sum which fits the data always in the same way. So is this clear? So it is crucial that these additional terms, new additional terms in the equations of motion, have the same leading UV sensitivity as the loop integrals in the standard perturbation theory. Because this is what allows us to basically combine the two and get a result which is consistent and independent of the choice of the cutoff. And so you see, these type of things were missing before. And so when we were seeing this plot where we see that the usual one loop and two loop calculation doesn't go through the data, it was because it was missing this additional three terms with this particular momentum dependence. And when we add them, then things should presumably be fine. So let us check if this is what happens. Okay, so now I'm going to go through like a couple of plots and show like how things look like. So this is now looking at some kind of a reality check. So first of all, let me explain what is in all of these plots because it will keep appearing. So I want to make sure that everybody understands what is plotted. So here we have on the x-axis, we have the wave number k. I told you that at redshift 0, you can think that the nonlinear scale is around k of 0.3, like at redshift 0.6, which is a bit earlier period in the history of the universe, the nonlinearities are a bit smaller, so the nonlinear scale will be pushed a little bit further. So let's say it will be somewhere between 0.3, 0.4. It doesn't really matter. Now, what is plotted on the y-axis is like the ratio of various models that we are going to use and the nonlinear data. Okay, so the nonlinear data are taken from an n-body simulation which has a huge volume. The volume of this n-body simulation, if I remember correctly, was something like 600 gigaparsec over h cubed. It was a huge volume. Like it's much bigger than the observable universe. The reason why I'm using this huge volume simulation data is because I want to have a tiny error bars so that we can really see the real difference when we start including different terms. So basically, if your model was perfect, if you really knew how to predict the full nonlinear matter power spectrum, then these data points will be scattered around one, because you will just get that your model is equal to the p nonlinear, and therefore the points will be scattered around one. Okay? The fact that the points are going away from this straight line, which is where the ratio is equal to 1, means that your model is not good. Okay? And then looking at these numbers, you can estimate by how much your model is wrong. Okay? So for example, this thing here is 1%. So if this ratio is, let's say, 1.01, this means that there is a 1% difference. So, and here I'm labeling it also on this side to keep it in mind. And so you see these error bars in each individual k-bin are much smaller than 1%. We're looking at a very precise simulation, and we're going to do a very precise comparison to the theory. Okay, so then let me next explain what are these orange and red curves. Okay, I told you that now once we once we write down everything consistently in terms of the long wavelength fields, we have basically two expansion parameters. One is the variance of the density field, the other one was the derivative expansion. And then we can estimate how big are the contributions from, let's say, next to leading order in perturbation theory compared to the linear theory, which we call the one loop power spectrum. We expect it to be roughly of this size. So what does it mean? It means that when you come to k of 0.1, you're expecting the size of this one loop term to be like a few %. or 10%. I don't know if you just extrapolate here, it will be order of a few percent. Okay. Similarly, we are not going to do the two-loop calculation, but you can do it, and you can estimate how big are these two loops. And this is the curve for the two-loop term. So, for example, we're expecting that at k of 0.1, the two-loop term is much smaller than 1%. It's basically a negligible correction because we're on very large scales. But as we go to smaller scales, the two-loop term is becoming significant. So, for example, you see here that at k of 0.2, it is roughly 1% correction to the power spectrum. Okay. And so finally, let me say, how do I exactly get these data points? Well, the data points are, as I said, the ratio of the model and the nonlinear scale. The model in this case is just the linear theory. So in other words, if you take the linear matter power spectrum and try to fit it to the nonlinear matter power spectrum of simulation, and you make the ratio of the two, this is what you're going to get. So on very, very, very large scales, so this is not that this is a linear scale. So this is basically k of 10 to the minus 2 or something like that. On very, very, very large scales, it seems that the linear theory is still a decent approximation to the truth. Okay? Simply because the nonlinear corrections are very small. They're expected to be very small, so you will not see the difference. And even in this humongous simulation, in the first few k beams, linear theory still kind of reproduces the nonlinear matter power spectrum. However, as you go to higher k beams, you start seeing that this ratio between the linear theory and the nonlinear theory is getting larger and larger, and the typical size of this ratio agrees with the one loop expectation. Eventually, of course, things go down and they go up again, and so. But it is somewhere within this band, because this one loop error means like absolute error, so it can be plus or minus this size, but you're within some band of the one loop prediction, and everything makes sense. So this is, we expect that linear theory is wrong. We expect that the corrections of the order of the one loop, and so we are expecting that if we add one loop terms, things are going to look better. Okay. So is it clear what is in these plots? I'm going to show several of these plots. It's important that you understand all these lines. So what will be fixed is the y-axis, the x-axis, these two estimates of how big are the one and two loop terms. What is going to be different in each of these plots is that I'm going to change the model. So for example, here is the linear theory. And here is what happens if instead of the linear theory, we use what we computed last time, which is just one loop corrections, which have only P13 and P22 loop diagrams. So this is what people used to call the standard perturbation theory one loop result. Okay. And in this case, you see that there is a little bit maybe of the improvement on these very large scales, but again, the model deviates from the truth. And crucially, it doesn't deviate from the truth at the level of the two loop that you would expect if the perturbation theory would be correct, but actually this deviation is significantly bigger. So this is the equivalent of what I was showing you at the very beginning of this lecture, that there were these several lines which were never going through the data points. They were always deviating from the truth. Now, then I told you that the way to fix this, at least one part of the problem, was that we didn't have the correct equations of motion. And when we include these additional terms in the equations of motion, the hope is now that the result will be indeed look better, and we're going to bring the difference between the linear theory plus one loop within these two loop error bars. Okay. And sure enough, when you include these additional counter terms, which effectively here is only one counter term, which is CS times K squared times P linear of K, because the other one is very much suppressed, then the picture makes perfect sense again. Okay. So now we're seeing the ratio of the theoretical model compared to the full nonlinear simulation power spectrum. And we see that now on all these scales, we have an almost perfect agreement between the theory and the data. And the disagreement is indeed well within the two-loop estimate. So if we were to add also the two-loop power spectrum, then we would push these agreements to larger scale, to smaller scale. I would like to emphasize that there is a huge gain here. Okay, so let's go back and take a look at this. So if you wanted to use just the linear theory to do data analysis, let's imagine that somebody gives you this box and asks you, can you measure the amplitude of the matter power spectrum? The linear theory will break down somewhere here. So already, oh, sorry. So somewhere here, the linear theory breaks down, and this is the Kmax in your analysis that you can use. So you will be able to infer the amplitude of the power spectrum only from the first few K-beams, which have a largest error bar, and therefore your measurements will not be great. Okay? But having a better model, which now includes using the right equations of motion, it allows you to push further. Actually, your Kmax goes all the way up to here. So you see, you're extending the range of validity of your theory quite a bit. And let me remind you that the signal to noise for any observable, more or less, scales like the volume times Kmax cube. So for example, even if you have an extension in the range of scales by a factor of 2 or 3, let's say, in the Kmax, you see that the signal to noise is increasing as a cube of that factor. So it's really a big gain in how well you can measure cosmological parameters using this nonlinear model. Okay? So is this clear? So you see, with a relatively small and simple modification, we were able to gain a lot. Now, this modification at the end of the day, in terms of the functional form that we are adding to our modeling, is simple, but conceptually, it was a bit difficult to get to, and these issues were puzzling people for a very long time. Are there any questions about it? Yeah. Sorry, I didn't understand. The blue points. Okay, the question is like, what do blue points correspond to? So the blue points are the ratio of the model and the full nonlinear matter power spectrum. In this case, the model is the linear theory plus one loop, including EFT corrections. Why do they have the error bar? Because it is the ratio of the model to the full nonlinear theory. And the nonlinear theory is just measured from simulations. And measurements in simulations always have some error bars. So this is why. So this is just like the usual cosmic variance error bars plus some noise. You can see that this data is a bit noisy. And you can see that by the fact that the error bars do not uniformly shrink. But sometimes you will have error bars which are smaller between 2 points which have the larger error bars. Okay? This may seem as a surprising thing. Indeed, the reason why this happens is because here, the way that this is obtained is not as a single simulation of 600 gigaparsec cubed, but is obtained by basically averaging 10 simulations, which have all 660 gigaparsecs cubed. So when you do the average of 10 simulations in each K-beam, sometimes, and then you estimate the final error, sometimes it may happen that the scatter between 10 simulations in this beam happen to be smaller than the scatter in the other neighboring beams, and so these error bars are not uniform. But yes, so in all these plots, the blue points are always the ratio of a model which is written in this transparency and the full nonlinear theory. And for example, here the model was the linear theory, and if you just use the linear theory as the model, then there is a big discrepancy. So now, as we refine our theoretical model, the discrepancy is much smaller, and we see that there is a better agreement. Any other question? Which W? Sorry, this is not. I know that it looks like W because my pencil just fell, and like now it doesn't write as it should. This is volume, of course. The signal to noise depends on, like this must be some, the signal to noise ultimately is just the number of Fourier modes. Remember, this is the number of pixels in your map or the number of Fourier modes in your K-space. So the bigger the volume, the better for signal to noise. And the higher K max you go to, you have more Fourier modes you can fit in this volume. So the better it is. And it goes like K max cube, of course. So here the volume, let's say in a realistic analysis, the volume is more or less fixed until you build another survey. And then pushing to higher K max is the only way to get better error bars. And so I'm just showing here that going from linear theory, which would stop around here, to the one loop model which stops around here, there is a big gain in the range of scales, which when you cube it, gives you a lot more power, constraining power than just using the linear. Yes, these error bars I have just cosmic variance error bars, which means that in each K bin, so what does it mean? Like imagine you have a big simulation box, then of course the lowest wave numbers you can test, there are only a few of them. So you will have a big scatter between these points, and there is a big error bars. As you go to smaller and smaller wavelengths or higher and higher K, you have many, many, many more of these Fourier modes. And then you basically your error bar on what is the amplitude of the power spectrum in this high K is shrinking. So these error bars are shrinking, but here I'm talking about the signal to noise of the whole analysis, where you basically sum up all these. For example, imagine that you want to measure the amplitude. Then you measure the amplitude in this bin, in this bin, in this bin, and you sum up all of them. And then when you sum up all of them, the total signal to noise for one cosmological parameter, let's say the amplitude of the power spectrum, is going to be given by the total number of Fourier modes. Well, these error bars depend on the number of the Fourier modes, but in each cell of the K binning, okay? Yes. Well, it will just deviate more and more very significantly, because the perturbation theory doesn't tell you anything about this high K part. And why is it oscillating is because life is very difficult, and this is very sad. So you see, I'm going to tell you now, for the rest of this lecture today, we're going to see why is this still oscillating, and we will try to fix that as well. So hopefully by the end of today, there will be no more oscillations. But you're absolutely right. This is indeed, so you see, globally, things seem to be fine. I think that we achieved something very nice. We see that we can basically make predictions, which is very precise. So pay attention, this is 1%. So you're really talking about sub% precision, like going to relatively high K. So it's a difficult task. It's not so easy. So overall, like we have a percentage-like prediction on all scales. But it is true that it's very annoying that we are seeing this thing. Okay, very bad. So what is this? Well, this is our old friend. Clearly, these oscillations are some. So first of all, okay, let me see. So these little oscillations are, of course, the BAO wiggles, right? This is something related to the BAO wiggles. They have the correct frequency and correct position. However, these are not full BAO wiggles. The full BAO wiggles are between 5 and 10%. Okay, these oscillations are only like a fraction of that. They're like a percent level fluctuations. So what does this mean is that we are getting the BAO wiggles roughly correct, most of it maybe, in this nonlinear model, but there is some residual BAO wiggles we are not getting right. So this model doesn't get the BAO wiggles right. And the other way to see this is to do the Fourier transform and take a look at the correlation function. And this is what I was showing last time and at the beginning of this lecture. So in the correlation function, and again, these are simulation points. This is the nonlinear result. the solid black curve is the linear theory. So we know that there's a broadening of the BAO peak in the nonlinear evolution. But if you take even this full EFT nonlinear matter power spectrum and do the Fourier transform, you're going to get this dashed line. So you obviously, we are not getting the wiggles right. There is something completely wrong about the BAO wiggles. And this is nothing to do with small scales, because we're trying to get some feature on very large scales. We're trying to get it right. And modifying, adding these counter terms, dealing with these EFT coefficients and so on and so forth, this was changing how the power spectrum looks like at high K. Or if you do the Fourier transform, this will tell you how the correlation function is affected on small scales of, let's say, order 10 megaparsecs. Here we're talking about the correlation function at 100 megaparsecs. So clearly, this issue with oscillations is not a small scale problem. It's not a UV problem, but it is something else. And before we move on to this something else, I can ask again, are there any questions still related to this plot? Yeah. Okay, so you're asking, the question is about the relation between K max, and I think that you're really talking about some angle separation on the sky, which I think, I don't know how to, because you see, to convert some distance to angles, you also have to know, some physical length to angles, you have to know how far away you're looking at. So yeah, so at this particular redshift, that much about projecting. So okay, I think that, so don't use the word projection anymore. I think that I'm not the host. I cannot share because it says here that I'm not the host. So maybe things were interrupted. And, but let me say this. I think that the way we usually think is more like in real space and Fourier space before we convert to angles. So the conversion that is useful to have in mind is that roughly scale that corresponds to this K is 1 over K. So for example, if I go here to K of, let's say, 0.3, this roughly means 3 megaparsecs in physical scales. And then depending on the redshift and so on and so forth, it will be a particular angle in the sky, which I don't know on top of my mind. Well, if you put Kmax of 0.5, this is 2 megaparsecs. If you put 0.3, it's 3 megaparsecs, roughly speaking. So it's like a few megaparsecs. Yeah, this plot was, oh, sorry, no. This was wrong. Yeah, I'm doing it in a second. Well, sorry, this conversion doesn't depend on the redshift. So for example, if you have Kmax of 0.3, this means, let's say, 3 megaparsecs in all redshifts. Then if you want to convert something at redshift 0.6 to some angles, then you have to know the distance. Yeah, you're talking, but this correlation function, you're imagining correlation function in terms of like some kind of separation of the sky and so on and so forth. You project it and so on. I'm talking here about, so you see, I don't know, because this involves the distance to the particular redshift, which I don't know on top of my head. How much is it to the 0.6, let's say gigaparsec or so, few gigaparsecs. So, but in real space, this will correspond to a few megaparsecs. This Kmax that we're going to. Any other question? Yes. So the question is for the zoom that since this volume is unrealistically big, does it mean that in the realistic survey the error bars will be much bigger? And then why do we care about all this precision? Okay, so let's see. So this volume is 10 times bigger than, for example, what DESI or Euclid will have. So the errors will be only 3 times larger, so not so much larger in the realistic surveys. But then when you do like a next generation surveys, they're going to start approaching to a significant fraction of this volume. So we can imagine, for example, that the mega mapper or like even some more futuristic experiment can map, let's say, 1/200 gigaparsecs cube, and then this is like only 3 times smaller volume than this unrealistic example. And so even for practical, in practice, I think that it's nice to see that we can that we can test our theory in these kind of setups, and it gives us some idea where should we stop. And for example, if you want to compute the Fisher matrix that Cora was talking about, one of the main inputs is like where do you stop in your analysis? What is Kmax? Now, more academically, the reason why I'm showing this is because here in this exaggerated volume, you can very clearly see every single mistake that you're making. And I think that the purpose, I'm going to show tomorrow what was the real purpose of running this gigantic simulation. But for the purposes of these slides at the moment, you can think of it as a very precise tool to really see like the issues, all the issues that you may have, and try to fix them the best that you can. Because if the error bars were much bigger, maybe you would be happy with this plot and miss the. Yes. The horizontal line would be equal to 1 if your model would be as good as the full measured nonlinear method power spectrum. Measured in simulation, yes. So if your model is perfect, these points will be scattered around 1. So this measures by how much this model is not perfect. Okay, so this, I think you have to, like, there are ways to convince yourself, but this is like, yeah, you have to take a look a little bit more carefully in the derivation, equations of motion. How do you expand this, like, stress tensor? But the question was like, how do you know that, for example, here we saw that at the one loop level, the leading UV divergence was exactly, has the same shape as the counter term, and it will be absorbed exactly in one parameter. But if you go to, let's say, higher order perturbation theory, or consider other correlation functions, how do we know that the counter terms will always absorb all the UV divergence? And this is going to happen always. In a consistent effective field theory, it must happen. You cannot have, because if it doesn't happen, it means that there is some calculation that you can do, or some higher loop or higher endpoint function diagram, which doesn't, where there will be some UV dependence, so you will not be observed. The only thing that it means that you're missing some counter term in your equations of motion. And in fact, I think that people have discovered some missing terms this way. One way to generate basically all these possible counter terms is to try to compute all possible observables and see what do you need in order to absorb. Because by construction, you cannot have a consistent theory which has some dependence on the UV. So it will always be the case that at all orders in perturbation theory and for any observable, things will be consistent. But it can be a bit tedious to prove this explicitly. As you go to higher order calculation, things get more and more complicated. But conceptually, it will get. Okay, let me maybe, I see that nobody asks about equations, but the plots like are very entertaining. Maybe I should have shown only plots. Yes. Oh, I didn't run this simulation. This was done by Takahiro Nishimichi in Japan at IPMU. Sorry, not IPMU. I think he's now in Kyoto. And he used some super nice supercomputer to run. It's a huge number of particles. So these simulations have very large volume. It is a 4 gigaparsec on the side, but they are good enough to resolve dark matter halos necessary for the making Boss-like mock data. I really don't know. Yes. Yes, here also you have to, basically your cutoff in some sense is the typical interparticle separation because you don't probe anything smaller than that. So people use the grids when they do FFTs and when they put particles and so on and so forth. But this scale is much smaller than what we are considering here. So like we are safe. It's nowhere close to this K of 0.4. It will be like maybe K of 4 or even 40. Like it is much smaller. All right, so here there is like the issue with the BAO, and which is still there. And let me briefly, because I have only 15 more minutes, tell you what is the final thing that we have to take into account in order to fix this problem. So first of all, where does this problem come from? And so it is well known, and probably you have seen this many times, that what causes this spread of the BAO peak. So for example, you see that in linear theory, the peak is very sharp. When we look at the nonlinear data, this bump is still there, but it's much milder. And so what causes the spread of the BAO peak are, you can imagine that, like just for the purpose of the cartoon, that you have some position of a galaxy here. This BAO peak means there is an excess to find another galaxy in a certain distance of, roughly speaking, 100 megaparsecs. And so now, if you imagine that you paint some particles at this distance and then you do some nonlinear evolution, we all know very well where does this spread come from. It comes from the fact that there are some not so long wavelength fluctuations which are producing some like motion of these particles in random directions. And so if the particles move in random directions, when you average the things at the end to compute the 2-point function, you're going to see that actually the feature has been broadened, okay? Because now if something was very sharp, imagine in some ideal situation a pure delta function. So everybody is at the same distance. If they move in random direction, when you average after a while, they're going to be producing some broader feature, okay? So clearly, what is causing the problems and what is causing the broadening of the BAO peak are these so-called bulk flows, these large displacements where particles are moving around in the background of these long wavelength fluctuations. So now one simple way to estimate how far the dark matter particles move due to this is to do it in linear theory and take a look at this linear equation. And remember that basically what this means is that the time derivative of delta is proportional to the velocity. And so if you want to estimate the displacement, how far the particles move, which I'm going to denote by this psi1, which is some integral of the velocity over time, then we see that this equation implies that this displacement is simply given in terms of the overdensity in this way. Okay. Now I'm denoting this. Maybe some of you know this notation of psi1. This is just the Zeldovich displacement, and indeed, this has to do with the Lagrangian perturbation theory. Maybe I will say something about it at the end or tomorrow. But for the time being, this is just how far the dark matter particle moves given some overdensity delta, which we obtain from this simple linearized equation. Okay, so then we can ask the same way as we were computing before, what is the typical size of fluctuations? We were computing the variance of the density field. Now we can ask, what is the typical size of this displacement? And you may naively think, well, if the variance of delta is small, the typical size of fluctuation is small, then also this displacement must be small because they're proportional to each other, right? However, this is not so simple, okay? And let me now explain why. Perhaps I can do a little calculation just to show you again, to remind you how to do these things. So for example, we want to compute the variance of this field. Well, the variance of this field is just going to be, so what is psi1? We want to do psi1 squared, which means that when we go to Fourier space, there will be integral over k1, there will be another integral over k2, because we have two fields. Here we are going to have minus I k1 over k1 squared dotted with minus I k2 over k2 squared. There will be a delta of k1, delta of k2, and then of course, e to the I k1x, e to the I k2x, and then expectation value. So all that I did is to take this product of two fields in the same space-time point. This is psi1 of x dot psi1 of x, and I wrote it as a product of the fields in Fourier space. Now, when the expectation value acts on these two density fields, it is going to give you 2 pi cube and then Dirac delta of k1 plus k2. And when you do one momentum integral to get rid of the Dirac delta function, then you're going to get the final answer, which is that this is equal to 1 over 2 pi squared, and then the integral of d of k times p of k. Okay? So remember that in our notation, this means d3k over 2 pi cubed. So the delta function will get rid of one integration. But in the other integration, the measure is still k squared dk. However, because you have one extra power of 1 over k squared in this product, the final integral will be just d of k times p of k. Okay? So now note that this is very different from what we had before for the variance of the density field. The variance of the density field had similar expression, but it was like k squared times p of k. And this k squared was very important. It meant that it really gives a very small weight to the power spectrum on large scales, and most of the variance of the density field in real space comes from small scales. And so as you go to smaller and smaller scales, the fluctuations in real space were getting larger and larger, and this is our usual intuition, that on small scales, the density field has large fluctuations, and on large scales, the density field has small fluctuations. However, when you take a look at the variance of the displacement, since there is no k squared multiplying p linear, it means that this integral picks up most of its contribution from scales around the equality scale. And indeed, if you remember the plot of the linear matter power spectrum, basically you're just integrating this function over k, and of course, most of the contribution will come from this scale. Okay? So this means that even though the fluctuations are large on small scales, the displacement that dark matter particles experience mainly come from the fluctuations on large scales, because the displacement comes with these derivatives, which introduce extra powers of momenta, which change this naive picture. That naively you may think the displacement is proportional to the fluctuation. The bigger the fluctuation, the bigger the displacement. This is not true. Okay, this is one of the things that is not true. And so I think that I wrote it somewhere, maybe not. Let me tell you that the typical displacement is roughly 10 to 15 megaparsec over h. So this is much bigger than the few megaparsec that was our nonlinear scale. So And now you see that there is some large parameter in our theory which naively looks to be proportional to the, naively you may say, I can treat this perturbatively. This is only something that has to do with the perturbations of delta. And indeed, we were treating it perturbatively so far. But actually, the variance of this displacement is very large. It is not a few megaparsecs, which would be fine, but it has a new scale, which is like 10, 15 megaparsecs, which is a much bigger scale. And therefore, this parameter cannot be, even though it is proportional to the density field, it cannot be treated perturbatively. It has to be, in some sense, treated in a different way. Now, in perturbation theory kernels, I already told you about this, but let me remind you that in perturbation theory kernels, we were seeing, and I told you that the physical meaning of these terms in this limit when momenta are soft compared to some momentum k, that these terms had to do with the displacement of dark matter particles. You remember, somebody asked me, what is the physical meaning of this middle term in the second order perturbation theory kernel? And the meaning was exactly this, that is a term which is producing displacement. And now we see that these terms, in principle, even though they're proportional to, say, delta square, delta cube, and so on and so forth, they seem to be perturbative in delta. Because of this particular momentum dependence, they can lead to some large parameter, and they have to be dealt with. And here I'm writing what are the most leading and the biggest contribution from each of the perturbation theory kernels, and the fact that these coefficients are 1/2 and 1/6 and 1/24 if you go to the fourth kernel is not by chance, but actually these terms can be actually resummed nicely into an exponent, and I'm going to show you that in a minute. So you see the conclusion here really is that we have these large bulk flows which can perturb the density field quite a bit on scales of 15 megaparsecs, 10, 15 megaparsecs, on very large scales. These large bulk flows are not induced by small scale physics, which is shooting particles far away. They are induced by the free fall in the gravitational field of the long wavelength fluctuations. And therefore, even though these bulk flows are messing up our density field, we can compute how they operate because they have to do eventually with large scales. Okay? And this procedure in which we do not treat these bulk flows perturbatively, but actually we resum them in the exponent, is what is called infrared resummation. We're talking about infrared because we are talking about low K modes, large wavelength fields, and resummation because we are resumming all their contributions because we just know how to compute it. Okay? So now I think that there is one thing which now may seem very puzzling to you, because I was always telling you that the nonlinear scale is a few megaparsec, but now I'm telling you that there are these large bulk flows which move things around, like not coherently maybe always, on the scales of 10, 15 megaparsecs. So how can it be that the nonlinear scale is like, let's say, a few megaparsecs? In other words, why we do not see these effects of these large bulk flows much more dramatically in cosmological correlators? And the reason why we do not see them much more dramatically is because a significant part of these bulk flows actually cancels when we talk about correlation functions. And I already did this example when we were doing this simple calculation of the bispectrum, the leading order 3-level bispectrum in perturbation theory. But let me remind you that if you consider the bispectrum, I was telling you this soft limit when one of the momenta is much smaller than the other. And so this mimics the situation in which you have one long wavelength fluctuation, which is displacing the other short wavelength fluctuations. Then the leading, if you want infrared, sorry, this is full of mistakes, and good that I spotted it. Of course, this is q squared. So the leading contribution, which goes like 1 over k over q in this limit, so these terms are presumably very big, there were 2 different contributions. And back then I told you that because in this limit, when q is very small, k2 is approximately minus k1, then for example, this term here will have the opposite sign compared to this one and similar magnitude, and they will cancel. Okay? So I was telling you that the effect of these large bulk flows essentially the biggest part cancels, but we want to be a bit more careful, because if it cancels completely, this means that there is no effect. So then what is happening with this BAO, okay? So the reason why this doesn't cancel perfectly is because we still have these parts here where we have momenta K1 and K2. And if you want, like, we can write this in a little bit more symmetric way. We can do a change of variables in which we say that K1 is equal to K, let's say, plus Q over 2, and K2 is minus K minus, sorry, I think that this is wrong, Q over 2. So now we see that K1 plus K2 plus Q is still equal to 0, which must be the case because we are by the overall momentum considering delta function, this must be the case. But now we have a little bit more symmetric way to write these two contributions. And basically, we will see that this sum becomes 1/2 K dot Q over Q squared, P of Q, and then we have P of K minus Q half minus P of K plus Q half. And now you may say, well, if Q is very small, I can just Taylor expand the power spectrum, and this will be equal to 0. So cancellation is still there. But the question is, can we always do that? Can we always expand this? Can we expand? And the answer would be not always, okay? Not always. And this exactly has to do with this BAO peak. And so let me now see what to do, because I think that I need 5 more. Can I take 5 more minutes? Is it acceptable or not? Because I would like to finish this today, and then maybe we start tomorrow with it. Yeah. Okay. So so I will come back to this question, can we expand? But let me say that, roughly speaking, yes, and it will be clear in a moment in what sense. So in these endpoint functions, there will be no dramatic effect due to these bulk flows. There will be something, which I'll discuss in a moment. Let me just say here also that a similar type of cancellation between large contributions from these bulk flows happens also when you compute loops. So we were focusing, here I'm again showing various loop contributions. And so, for example, take a look at the green curve, which is P13 diagram. So we were seeing, for example, that P13 in the low K limit goes like K squared times P linear. And this is exactly what you're seeing here. But now, on the other hand, if you focus on the high K limit of P22 and P13, you will see that each individual diagram is huge compared to their sum. I mean, if you keep going to higher and higher Ks, you will see that this behaves like this, and this goes down. So there are many of orders of magnitude cancellation between individual contributions to the loop and the sum of the two terms. And the reason why this happens is because each of these individual contributions is sensitive to these bulk flows, but when you sum them up together, they cancel almost perfectly. And again, they cancel almost perfectly for the reason I already told you last time, that basically what these bulk flows do, whenever you do this calculation, you're somehow comparing how two different things fall. And since the bulk flows are moving everybody by the same amount, this like difference basically is artificial, and the equivalence principle things have to cancel. Okay. And finally, let me come back to the question, when can we expand? So we can expand only if the power spectrum is very smooth on the scales of Q, okay? So then we can always write this Taylor expansion, and indeed the cancellation will be perfect. So for the smooth linear power spectrum, this cancellation is always perfect because we can always do a nice Taylor expansion. However, if the power spectrum has some features, then you do not necessarily can expand. And indeed, the linear power spectrum in lambda CDM does have features. So there is a smooth part, which is roughly speaking some broadband, and then there is a wiggly part, which has to do with the BAO wiggles. Okay. So this wiggly part has some characteristic frequency, which is like the BAO scale. And so even if Q is, let's say, much smaller than K that you're considering, but it is larger than 1 over LBAO, you cannot do a Taylor expansion of the sign. In that case, things are not going to work. Okay. And so in this difference that I was showing before, you cannot simply expand the power spectrum, and therefore there will be some contribution of these large bulk flows which affects features in the power spectrum. Physically, again, what this means is that if you have some fluctuations whose wavelength is shorter or comparable to the size of this BA ring, they are going to move, not in a coherent way, these particles, and they will cause the spread of the BA peak. So these two pictures are just the same story, one told in real space, and the other one with this expansion told in Fourier space. Okay? And so what we then have to do is to resum all the terms that cause the bulk flows, and I will stop here. And this resummation formula is relatively simple. I don't want maybe you to look at all details, but let me just say that schematically, what happens is that the smooth part of the power spectrum remains the same as before. We have the linear theory and the loop contributions with DFT corrections and everything. And because the smooth part is not affected by these large bulk flows. However, the wiggly part of the linear power spectrum, where the BA features are, is going to be affected. And there, we have to take into account all possible contributions from these long wave displacements. And if you do the math, you will see that basically you can write down some formula like this, where what sits in the exponent in front of the wiggle parts has to do with basically the variance of this displacement with some little extra details, which you may read about in the notes and in the papers. But the procedure is really this. So this is what is infrared resummation. Infrared resummation is correcting for these large displacements which affect the features in the power spectrum while keeping the smooth part intact, okay? And let me just show you, then once you include this infrared resummation, take it into account, then the difference between the true nonlinear dark matter and your one loop model where you correct for these effects in the feature becomes much nicer, and there are no more residual BA wiggles in this difference, okay? So now this looks very good because the one loop model works very well up to where you expect it to work, and even on larger scales, this difference is not a dramatic difference. So we have finally achieved our goal to have a model which consistently can predict things. We can predict it very precisely. We can, in principle, refine it. If you include two loops, this will be flat all the way up to here. And we understand what part of the solution was missing in the naive perturbation treatment. There are large bulk flows that can produce a large displacements in the dark matter density field, and therefore they have to be taken into account, but not for the broadband, because there they always cancel. They have to be taken into account only for the features. And sure enough, when you do everything as you should, then this is what you get. A very nice curve will go through all the data points, even in the correlation function. Okay, so now everything makes sense. Everything is very good, and I will stop here. And tomorrow, we will see how this story extends to bias tracers and redshift space, and then I will show to you how does it work in practice. I'll stop here. Thank you. Okay, so let me, since we are super late, let me just say that this splitting into the wiggly and non-wiggly part of the linear power spectrum is a bit arbitrary, but the result does not depend on the way you split. You can show rigorously that whatever split you choose, the result will be the same. The split should be roughly that you should somehow interpolate, if you want, the smooth part and look only at the residual BO wiggles as a wiggly part of the power spectrum. All right.